So welcome to the HVAC-Engineering-Techie channel. This is the channel where we talk all things HVAC, from engineering design, construction, equipment, systems, test and balance extensively, controls, and system performance. So these videos are intended to give you a basic education to help you advance your career. So today's lesson is on airflow and pressure calculations that are used to figure out how much flow we have on air. This is an air equation lesson. But before we get into that, if I could ask you to do me a big favor, and that is to hit the subscribe button, become a subscriber to the channel, and hit the like button. Now, none of that costs anything. It doesn't cost you a thing. And I will never bug you. I don't have enough information anyway, but I wouldn't do that anyway. So the reason I'm asking you to do that is Google uses that to evaluate how well this video is doing on their platform. So that would help me a great deal if you would subscribe. And there are some benefits to being a subscriber that are coming in the future, where I'll be answering your questions. And so be a subscriber. That would really help me, and I would appreciate it. So let's get started on airflow and pressure. All right, so we're going to start talking about airflow calculations. So the first thing we need to talk about is air velocity pressure. To do a lot of these calculations, we have to know the velocity pressure. And to do that, we have to calculate what that is, because in a duct, it has two kinds of pressures. It has static pressure and velocity pressure. Static pressure is the pressure of the air pushing against the duct, trying to get out of the duct, kind of like a balloon. When you blow up a balloon, that air in a balloon is static pressure. But also there's velocity pressure, and the velocity of the air, which is being pushed down the duct by a fan, the pressure of that air moving down the fan is called velocity pressure. And total pressure in the duct is velocity pressure plus static pressure. So we use two different kind of instruments to do that. The first is a pressure pickup, which just only reads the static pressure in the duct, because it's just reading the air going this way, not going this way. Then we have another probe that's curved and open on the end, that it reads total pressure. It reads the total static, and it reads the velocity pressure. So what we do with this instrument is we can take this one and subtract this one, and then we get velocity pressure. Well, we can also calculate it too. So here's the formula. It's VP equals V divided by 4005 squared. Now, velocity pressure is in inch pounds, or inch of water gauge, and it has a C. This 4005 is actually a C constant. It's a constant, and it's based upon 70-degree air. So it does change. If it's not 70 degrees, it changes. And here's the table for that. So if you have 100-degree air, it's actually 4117. So it's a larger number. If it's colder air, it's a smaller number. So that's how you can make this more accurate when you do it. But most of the time in air conditioning, the 4005 is a good number. So if you want to just find the velocity, it's 4005 times the square root of the velocity pressure. So there's how both of those work. Now this 70 degrees is also at sea level, and that's at 0.0749. So we can make some changes for density, but believe it or not, it changes very, very little. Remember, you can always convert into this. The Celsius term for this is PA, pascals, and it's 0.004 pascal. 1 pascal equals 0.004 inches water gauge. So there's a whole bunch of pascals in a little bit, so that can do that. So let's do an example. This is a velocity pressure chart, and you have a lot of these in your books. As a matter of fact, your balance manual actually has these, and it tells this is the feet per minute, the velocity, and this is the associated velocity pressure with that. Because, as long as the air is the same weight, it's the same. Well, okay, so let's say, what is the velocity pressure for air flowing at 2345? Well, it's going to be somewhere, let's see, this is 23, these are pretty small for me, so I have to get closer. 2300 is 0.3017, and 2300 is 0.3298, and 2400 is 0.3591. Now we could interpolate between that, but we can also just calculate it directly. So velocity pressure equals V divided by 4005 squared. So if it'd be 2345 divided by 4005 squared, and that equals 0.3428. And you can see that's in between these two numbers. So that's a reasonable answer for velocity pressure. So air changes per hour. Sometimes when you're working in a building, you need to know how many times the air is exchanged in the room. And that just simply means if you've got a certain amount of air going into a room and it going out of the room from a return grill, supply grill or return grill, how many times do you change the entire air volume of that room? So it's an easy calculation. Air changes per hour equals Q times 60 over room volume. So you will need to find the room volume. And the room volume is in cubic feet. And of course the Q is in CFM because that's the flow of the air. So, and ACH is the air changes. So let's say you have a room that's 30 feet by 12 feet by 10 feet and has 1200 CFM of supply air. What is the air changes per hour? Well, the room volume is this, the width times the length times the height, which in this case is 30 times 12 by 10, which equals 3,600 cubic feet. So that formula then for that is ACH equals Q times 60 over RV, which is 1,200 CFM times 60 divided by 3,600, and that equals 20 air changes an hour. Now, why we ever do that calculation is there are certain codes that require certain rooms to have certain air changes per hour, and operating rooms are one of them. There are other rooms, but air changes per hour is what you're looking for. Duct flow calculations. Okay, this is pretty easy. So the quantity of air, CFM, equals the area times the velocity. So the area is in square feet, and the velocity is in feet per minute. And that will give you the CFM. So if we look at an example, a 24 by 12 duct with an air velocity of 950 feet per minute, what is the flow of air? And in HVAC work, you need to know that the velocity range is from like 500 feet per minute to 2,400 feet per minute is reasonable duct flow. We don't do much high velocity duct anymore. Most everything is medium velocity or medium pressure or less, which means that we're in those ranges. So what is the flow of air if we have this 24 by duct at 950 feet per minute? It's Q, A times V, which is the width of the height. So it's 2 by 1 equals 2 square feet because we want it in foot. If it had been inches, you'd have had to convert, divide by 144, the square inches by 144 to get square feet. And then it'd be 2 times 950, which equals 1,900 CFM. So that duct will carry 1,900 CFM at 950 feet per minute. All right, let's go look at round duct. Round duct we use a lot, so you need to know the formulas for that. And the formulas for that is, we've covered this in our math course, but so remember, this is the diameter of the circle, this is the circumference of the circle, and this is the radius, which is the center point to the edge. So the area of the formula is A equals pi times r squared, and the circumference is pi times d, diameter. And pi, of course, we've talked about this before, is 3.1416, even though this is a rounded number because it actually is 1.5 and a whole bunch of decimals. But we have settled on 3.146 as a good enough for accuracy required for HVAC. So example, what is the airflow for a 24-inch round duct at 1,200 feet per minute velocity? So again, it's area times pi times r squared, which equals 3.1416 times, that's pi, times 1 foot squared, because this is 1 foot on a 2 foot duct squared. And that equals 3.1416 square foot, because remember, it's 1 times 1 is 1. So this is, its answer is pi. And then we take that equation before, the Q times AV, which would be 3.1416, which is a square foot of our 2 foot duct, times 1,200 feet per minute. And that equals 33,770. And by the way, a round duct is a much more efficient duct than a square duct. And the reason is because a round duct has the least amount of circumference per given area. A square duct will be more perimeter. And the reason of efficiency is because the perimeter is where the air meets the metal, and that's where the friction occurs, and that's what makes efficiency is how much resistance you have to the airflow. And round duct will have the least resistance airflow of any duct you can make. So that's why we use a lot of round. All right, now we got a different animal here. We've got flat oval duct. Flat oval duct was created because round duct are the most perfect duct, but they don't fit a lot of places. They're just too big. So they created flat oval duct to fit in spaces that square duct, that a round duct won't fit. And this is not quite as good as a round duct, but it approaches much more efficient than a square duct. So these are the formulas. Now these formulas were created by the manufacturer United McGill, which was one of the first to make these. And so I don't know what happened to my cursor. Here's my cursor. So you can see that these are a flat section and a round section, flat section, round section. So what you can imagine is if you take a full round duct and it's half of it's here and half of it's here and there's a square duct in between. So that's what the formula does. It calculates the area of the round areas and then the area of the square. So here's the flat oval. It's so if you take it here, this is the flat span. This is the minimum max span. This is the minimum span, and from that, and then this is the outside dimension. So the formula is the FS, which is this dimension, times minimum dimension, which is this dimension, times pi times minimum dimension squared over 4 divided by 144. That's the area. This is the perimeter, which is pi times minimum plus 2 times Fs over 12. And if you think about it, this pi means we're calculating that square footage. It's a simple concept. The formula is a little bit more involved, but that's what we're talking about here. So example, a 48 by 12 flat oval duct with a velocity of 600 feet per minute. What is a CFM? So we take this area formula, which is area equals, which we just talked about. And if you put these numbers in there, you get 36 times 12 over pi times 144 divided by 4, which is this minimum dimension, which is 12 times 12, which is 144, all over 144, and that all equals 3.786 square feet. So this 48-inch duct, 12-inch high, has 3.788 square foot. So now we take the Q times A times V, that simple formula we used before, and it becomes this number, 3.786 times the velocity, which was 600 feet per minute, which equals 2,272 CFM. So that's how we calculate the airflow on a flat oval duct. So now, what is the perimeter measurement for a 48 by 12 flat duct? Well, why would you ever want that? Well, just like we did in the round duct, what if you want to calculate how much insulation you need for a length of duct? You have to know the perimeter. So now we'll use this other equation, which is the perimeter, this perimeter equation, and by putting these dimensions in there, so we take pi times 12, which is the minimum dimension, times 2 times 36, which is this dimension, and divided by 12, then it equals, my computer's really slow today, 9.142 foot. So if you had a 100-foot of duct, you multiply that times 100, and you have the square foot of a 100-foot length of duct, this size we have here. This is a really helpful formula when you have flat oval duct. All right, mixed airflow equation. This is an equation you use a lot, especially if you're a tab guy. And that is, it tells you how to mix flows. So say if you're trying to find the temperature of an airflow, let's say you have so much supply air and so much return air, or a supply air and so much outside air, and you're mixing those two, and you want to know what the temperature of the air is going to the coil. This is the formula. It's real simple. It's the temperature of the outside air times the CFM of the outside air, temperature of the supply air times the CFM of the supply air, all divided by the total CFM. Now, the truth is, this formula works. This is really just a ratio formula. It works for anything. It can be dry bulb, wet bulb, CO2 concentration. It can be all kinds of things you want it to be because it's just a ratio. So we use it a lot here for a mixed air equation, which is the main one we do. So it can be enthalpy. It can be anything you want it to be. When we start talking psychometrics, we'll use this a lot, trying to figure out where our starting points are. So if a unit has 200 CFM of outside air at 98 degrees and 1200 CFM of return air at 82 degrees, what will be the temperature entering the coil? So this formula again, and then if you input those numbers into this formula, you get 98 times 12 times 200 CFM plus 82 times 1200 CFM divided by 1400 CFM, which equals 84.29 degrees dry bulb. So if we're trying to figure out what the temperature entering the coil is, we'll use a mixed equation to do that. So this is a really helpful equation, and you'll need to probably keep this in your memory instead of having to look it up when you need to know these temperatures. So now we start on the fun ones, the fan loss. Okay, so fan horsepower, the fan loss for horsepower is brake horsepower. Now what's the difference between brake horsepower and horsepower? Horsepower is usually the number associated with the motor. This is how much horsepower this motor will do. Brake horsepower is the actual horsepower being used by the motor, which is never equal to horsepower. It's always less, slightly less, or else your motor starts getting into trouble. So we have to figure brake horsepower a lot of time when you're doing a change to a system, and you want to make sure you don't exceed the horsepower of the motor. You have to do a brake horsepower calculation. And so brake horsepower equals CFM times static pressure divided by 6,356 times the motor efficiency. Motor efficiency, the hard one. You have to look at the motor to tell what the efficiency is. So if you don't know the motor efficiency and you're doing a theoretical calculation, just use 62933. I don't know who came up with that number. It's kind of a guess number, but I guess it's okay. It's also what I do a lot of times when I'm in my office calculating. I pick up my Granger catalog and I find that motor and look at the efficiency because it is listed in the motor ratings. And so you can do it that way. So this is a pretty simple formula. So let's do an example. A fan has 1250 CFM with a discharge pressure of 1.5 inches and a suction pressure of negative 0.5 inches. A fan efficiency of 68%. What will be the fan brake horsepower? Now remember, you basically, a 1.5 discharge pressure and a suction pressure -5 is not uncommon, but you add those two together, but without the sign. So it's going to be 2 inches total, right? So here we go. So this formula, again, CFM times static pressure over those numbers, and if you put these in there, you're going to get 1250 CFM times 2-inch static pressure, which is the total of those two. Divided by 6.356 times 68, which is the efficiency of the motor. And from that, we get, in our equation, 0.58 horsepower. So if this was a half horsepower motor, you're in trouble. If this is a 1 horsepower motor, you're in good shape. If it's a 3/4 horsepower, you're okay. Be better probably to be a 1, but, depending on what you're going to do with that motor. Okay, the second fan law for CFM, and this one might look familiar from our previous examples. Get to the formula. Here's the formula. It should have gone first, but it's CFM2 over CFM1 equals RPM2 over RPM1. So if that fan has 1200 CFM at 500 RPM, what will the CFM be at 600 RPM? So if we want to move that up. So if we take this equation and we input CFM2 divided by 1200, because CFM2 is the one we don't know, 1200 is the one we got, over RPM2, which is 600, the one we want to find out, and 500 is what it is now. So now we know what that is. So now we just simply cross multiply. And if you cross multiply this times this times that, you get 600 times 1200 equals 500 times CFM2. And then, of course, you multiply those out. 600 times 1200 is 720,000 divided by 500, and that equals 1440 CFM. Now, sometimes on these get to be really big numbers, but with a calculator, we really don't care. Get right? I mean, you got a good calculator. Big numbers don't scare a calculator. So example 2, a fan has 1200 CFM at 500 RPM. What would the RPM be for a 1600 CFM? So this is how we use it a lot, trying to figure out what we're going to do. We need more air. So what RPM do we need to do to get more air? There's our formula. Inputting this data into the formula, we get 1600, which is the CFM2 over 1200, equals RPM2 over 500. And we simply do the cross multiplication again. We get 500 times 1600, these two, times 1200 times RPM2. So that ends up being 800,000 divided by 1200, which equals 667 RPM. So this cross multiplication is the easy way to do these formulas. All right, another fan law. This is a fan for static pressure, which basically says static pressure 2 over static pressure 1 equals RPM 2 over RPM 1 all to the square. So that formula, then we can do to find out how to change the static pressure. Okay, I did move it around. I did rearrange that equation, so static pressure 2 equals static pressure 1 times those two numbers. But you really don't need that. You just need to cross multiply in this one. Let's say we have an example of fan has 1200 CFM at 500 RPM, same blower, and a static pressure 2 inches. What would the static pressure be if we took it up to that 600 RPM? We take that formula, which is a static pressure 2 over static pressure 1 over the RPMs, and we input this data into it. Now remember that when you have a number like this squared, it really is the same thing as the RPM2 squared over RPM1 squared. It's the same thing, that you don't have to change anything. So that makes it easy to cross multiply then. So then we cross multiply. So it's 600 squared times 2 times 500 squared times SP2. So that equals 720,000 over 250,000 SP2. So you divide 720,000 by 250 and you get 2.8 inches. Big numbers again, but still that's pressure. So remember before at 500 we were 2 inches. Now we've almost gone up another inch, 2.8 inches. So we've gone up quite a bit. So that's how you do a stand law for pressure. Now let's do another one. A fan has 1200 CFM at 500 RPM and a static pressure 2 inches. What would the RPM be if we went to 3 inches static pressure? So then we do that. We take the same formula. We input that data that we have here, because this is static pressure. So we have 3 over 2. 3 is the new one we want, over RPM2 squared over 500 squared. So then cross multiplying, we get 500 times 3, so we get 250,000 times 3 equals 2 times RPM a square. Now here's where when we want to find this, we take this number and we which is 750,000 times 3 equals divided by 2 equals RPM squared. So when we take that number and divide 750 by 2, we get 375. And to take this away squared, you have to do the opposite, which is a square root. So it would be 375 divided by square root. So when you have these powers, you have to remember, when you move that to the other side, it's the opposite. So it goes from a root to a square. So that 375 squared, do on your calculator, of course, is 612 RPM. So we went from 500 RPM to 612 RPM. Will now get us 3 inches static pressure. Now you'll notice that small changes in RPM make bigger changes in static pressure as a percentage. So you have to be careful on when you make changes that you don't get too high. Now remember, a lot of times in the field, you'll be doing more than one of these equations on the same thing. So if you needed to know what the static pressure was and the RPM was, now you may have to go back and do that brake horsepower one to make sure you're not over the horsepower of your motor. So these equations, of course, are very, very helpful. We use these all the time. You need to become really familiar with these. The next fan law is fan law for horsepower. Horsepower 2 over horsepower 1, same thing we've done before, except you do notice this is a cubed in there now and not just a square. So if a fan has 1200 CFM at 500 RPM with 5.2 brake horsepower, what would the brake horsepower be at 600 RPM? So there's a formula. We stick in our numbers, which is 5.2 and 600 over 500 cubed. So cross multiplying, we get 600 to the cube times 5.2, that number, times 500 cubed times HP2. So we get 1,123,123, big number, divided by 125 million SP2. remember on your calculator, you hit the cube functions, it's easy. It's 8.99 brake horsepower. So remember when we were fooling with this before, we just took a little bit RPM up, we took it up to 0.58 brake horsepower. Now it's really moving up. It's a lot. So instead of 5.2 brake horsepower, it's 8.99 brake horsepower. So before you might add a 7.5 horsepower. Now you're going to have a 10 horsepower to do that. So this is why this fan law is helpful. A fan has 1200 CFM at 500 RPM with 5.2 brake horsepower. What would the RPM be for 4 brake horsepower? It's going to be a lot less. So if we put that data in this formula, we get 4 divided by 5.2, RPM 2 over 500 cubed. And then if we go ahead and do our cross multiplication of that, we get 500 cubed times 4, which is here. 500 cubed and is the same on top and bottom. Equals 5.2 times RPM 2 cubed. And that equals, when you multiply that all out, that equals 500 million divided by 5.2 cubed to the cube root, because we moved the cube to the other side. And that equals, again, the calculator's got a button for that, so it makes it easy. It's 458 RPM. So instead of 500 RPM, which it was, we've gone down to 458 RPM. Okay, now duct pressure drop calculations. Now, when an engineer designs a job, he'll lay out a duct system for a job, and he'll lay out all the grills and registers and all the airflows. And then he has to calculate how much pressure the fan needs to push that much air through that ductwork. To do that, he has to do a pressure drop calculation. And nowadays, it's easy. They just have a computer program, stick the ductwork in there, and it figures that all out for them. But here's how you do it manually. I guess it's one of the advantages of being an old guy. I used to do all this by hand, so I do remember how to do all this stuff. I used to have computer programs also, but originally I did it all by hand. So the formula is total pressure equals C, which is a constant, times the velocity pressure. Again, we need the velocity pressure. Now, where do you get the C? Well, you need to look it up. And there are tables. ASHRAE has tables. And SMACNA has tables. I've always used the SMACNA tables. Maybe it's a good discussion here about HVAC in general. HVAC is an empirical science, which means they didn't figure it out ahead of time. They went out in the field and measured things and see what's happening, and that's created the science we use. So all I'm saying is that there are some sciences out there, they had theories way ahead of time, and then they tried to do tests in the field to see if they could support the theory. Well, in HVAC is the opposite. We actually seen it in operation, and then we went and figured out by testing that system, what the calculations were. It's an empirical science. So what SMACNA did is they went out, and we used to have standards on how to do this pressure test that were really not very accurate. And so SMACNA set up test rigs and tested every single type of fitting. There's a lot. And they created tables like the one I show you up here. This happens to be for a round, flat elbow like this. This is a table. And these are the C factors in this table. And they have a book, it's like an inch thick. It has all these fittings and all these different tables in it. That's what you use manually to try to look these all up. So what this is these are the values. This is the H over W, and this is R over W. So this is the radius, R, and that's over W, which is the width, the height of the thing. And H over W is the length times the height ratio. So you got those two numbers. So the R over W goes from 0.5 to 3. H over W goes from 0.25 to 6. Now, if you're over those numbers, you just divide it up into, cut the duct in half or something to do that. And the formula again is TP equals C times velocity pressure. So example, what will be the pressure loss for a 24-inch by 6-inch elbow with a radius of 6 inches and an air velocity of 1,800 feet per minute? So you find the velocity pressure for 1,800 feet per minute, which is 0.2020. You can either use a formula, you can look it up in a table. And it's easy if it's even. You can look it up on the table. But if it's not easy, it's easier just to do the formula. So remember, H over W is 24 over 6, which equals 4. So this number here, we're looking for 4, which is right here. And RW is 6 divided by 6, which equals 1. So we're looking for 1 here. So this is the C factor is 1 times 4, which is right there, which is 0.21. So TP equals C times velocity pressure, which would be 0.21, which is a C factor, times 0.2020. So they equals 0.04242, which is not much pressure. But remember, this is just one small fitting at a fairly low velocity. When the velocity gets higher, these get more critical. So this is how you do an exact pressure for fitting. So in a duct system, you would do it for a straight duct, you would do it for all these fittings, you'd add them all up, including the pressure loss through the diffuser, through the return grill, back to the system, and then you would get your total pressure. And then a smart engineer is going to add 10 or 15, 20% to that to make sure he has plenty of pressure for future changes or things that get built slightly different. And that's how we do this duct pressure test. All right, now altitude corrections are something you must do if you're working at altitude. So remember that this is the chart for densities. So here's the temperatures, and here's the sea level. Here's the levels. So at sea level, we get this 0.7049. Okay, so now we're going to talk about, there are two types of altitude corrections. One is for constant volume, which is for, remember that a fan is a constant volume device, and the CFM is the same no matter what altitude you are, but what changes is the weight of the air. And of course, the second one, so air density changes with a change in altitude, air due to the temperature of the pressure change. So example, now this is if you've got a fan. The catalog of a fan says it's 5,000 CFM at 2.5 static pressure at sea level with a 4.8 brake horsepower. What will the CFM at static pressure and brake horsepower be if it's operated at 6,000 feet? So the catalog data will change because the fan will change. So what happens, since the fan is a constant volume device, the CFM will be the same at any altitude, but the density of the change in static pressure and brake horsepower. And remember, as you go up, the density goes down. So basically, but these two go down. So the formula is static pressure 2 over static pressure 1 equals density 2 over density 1. This is a formula, it's basically just a ratio. So if you have static pressure 2 over 2.5 equals 0.06. See, okay, so this is density 1. Density 1 is 0.0749, which is here at sea level. And then at 6,000 feet, it is 0.06. So you're going to get that. It's going to be cross-multiplying again. So 2.5 times 0.06 times static pressure 2 over 0.0749 equals 1.9 static pressure at 6,000 feet. So at sea level, it's 2.5. At 6,000 feet, it's only 1.9. It's down. So brake horsepower, we do the same thing again. Brake horsepower 2 over brake horsepower 1 equals D2 over D1. So we take that ratio and we make it, it's 4.8 for the brake horsepower up here. It's 4.8 brake horsepower. And we're going to find a new brake horsepower over 0.06 over that same ratio. And you can cross multiply it again and you get 3.65 brake horsepower at 6,000 feet. So you see before it was a brake horsepower 4.8, and now we're down to 3.65. So you could use a smaller motor, but basically it's just going to use less energy. Now there is a second kind of altitude correction, and that's for a constant mass, where we want to have the same BTU. So remember that the last example, we had a CFM of that fan, and if it was doing cooling, at altitude, it won't do as much because the energy in the air is less at altitude, so it can't do as much cooling. It has the same amount of air, but it's going to have less cooling. So basically, we have to make a change. So example, a system at sea level has a 5,000 CFM and a total cooling load of 118,800 BTUH at a 22 degree delta T. What CFM will require to deliver the same cooling load at 6,000 foot elevation? So this is something that you need to check all the time. So it's CFM2 over CFM1 equals D1 over D2, the same formula. CFM2 over the 5,000 CFM over that same ratio, except it's reversed. If you notice, it's D1 over D2. So it's 5,000. We're going to cross multiply again. It's 5,000 times 0.0749 times CFM2 times 0.06, which means to do this much BTU, you'd have to have 6,242 CFM at altitude to do that same load. And that's a calculation we must do all the time, especially when I was commissioning a job. I would look at the equipment they're sitting up there and see if it can actually do the same load at altitude by running this calculation. Okay, specific volume of the air is a reciprocal of the density. So if 1 over 0.060, the air will weigh 16.67 pounds at, it will, 1 pound of air will take 16.67 cubic feet. Now down at sea level, it's 13.5. So it's a lot less, or a lot more air. It takes a bunch more air at altitude to make the same pounds per air. So BTU times sensible heat divided by 60 divided by S specific volume times CFM times delta T. So this is our heat equation you know before. So it's 0.244 sensible heat times 60 divided by 16.67, which is this specific volume, equals 0.087. So 0.087 times 6242, which is the amount of air we need, times 22 equals 119,000. So this was 118,000 BTU. So we got enough BTU, we're covered. Slightly higher, but good enough. So we're good to go. Remember, in these HVAC calculations, they are not perfect because they're based upon constant factors that don't have a lot of decimal places. So there is some kind of room in these calculations. So don't ever expect your calculation to be perfect. You can instead of using those factors, use the real number, and you can get a lot closer. But even then, there's too many constants and too many assumptions made in all these calculations to be perfect. So we know they're close, we're good to go. So another method is just to use a straight ratio. It's 5,000 times 0.07 by 0.06, which is just a ratio. So you take it divided, and that's 5,000 is 6240. So this is 6242, 6240, very close. Close enough. So you can tell you can do either way. And that's it for air calculations. And I hope that was beneficial to you. And please don't forget to subscribe and like. That would really help me a lot. Have a good day. Catch you on the next one.